Hi, everybody. Welcome to our discussion of gamma ray bursts, our last topic for Friday, November 13th, for class. And we are we're going to talk, give you a very short introduction to the concept of gamma ray bursts. In my edition of your book, this goes all the way back to chapter 14. This is for the Science 121 astronomy class at Luther College. I'm Professor Jeff Wilkerson. And so I don't know if maybe they've moved it. I would put it in a different section of the book for sure if I were writing the book. But it goes back to the end of chapter 14 in the edition of the book that I have. And so gamma ray bursts are just what they sound like. It was discovered that in the 1970s and 80s, it was discovered that there were very intense, very brief flashes of gamma rays coming what appeared to be randomly from across the sky. You can actually see that in slide 13 of your PowerPoint. That's the distribution in the sky. That's in galactic coordinates. And so that's an old way to view that in the sense that back when we thought that maybe they were coming from sources within our Milky Way galaxy. But you see, they come from everywhere. They're all over the place, and you look in any direction. And remember, we call that isotropic. So this is an isotropic distribution of gamma ray bursts. Now, typically, that means we would have to be in the middle of that distribution. We have to be not necessarily that there is a middle, but if they're in the galaxy, it would have to be consistent with the middle. There would have to be a halo of objects around us so that they looked the same in all directions. Unlike the globular clusters, for example, that we were looking at in lab, where you look one direction to see them because we're outside that distribution. Much easier to make an isotropic distribution if you're talking about things that are associated with distant galaxies, the universe writ large. So if you're talking about things that are cosmological, that have vast distances and are associated with the largeness of the universe, then the universe is the universe is isotropic. Let's not even say more or less. The universe is isotropic from our vantage point. We see this universe more the same in all directions. And so that means that things that are associated with the universe writ large would look the same in all directions, like these gamma ray bursts that you see there in slide 13. And so this is another example. We talked about adaptive optics earlier. This is another example of where the U.S. military was ahead of astronomers on this topic. They knew that the military, the spies, were interested in nuclear weapons tests, and nuclear weapons tests might lead to bright, intense flashes of gamma rays. And so there were satellites that were launched to look for these, to see if there were surreptitious nuclear weapons tests going on the surface of the Earth. And what they found was they were getting flashes of gamma rays from the backside of the detector. They're looking down at Earth, and coming from the backside were gamma rays hitting their detectors. And so they knew that there was something going on there from space. It took the astronomers a little while to catch up, but the astronomers finally figured it out and said that at the rate, I don't remember what the rate is now that we're gotten better at detecting these things, but maybe one a day, you would see a big, bright, intense flash of gamma rays and nothing else. That's what's really odd about this, is when they were first discovered, you didn't see any optical light, you didn't see any X-rays, you didn't see any ultraviolet, you didn't see any infrared, just gamma rays. And just gamma rays it's an odd spectrum to have, is to just be emitting gamma rays. And so we set about trying to figure out what these were. And so this is part of the astronomical history we're talking about. It's part of my personal history. If you see my copy of my PhD dissertation right here, it's development of imaging high-pressure xenon gas scintillation drift chambers for use in gamma ray burst astronomy. And so I may have told you previously I was working in neutron stars, and there was a lot of speculation at that time that these were associated with neutron stars, and we still believe that to a certain extent, but not in the same way we did at that time. And so I decided to shift over and to work on discussion of how we could use the detector I was developing, the instrument I was developing to measure gamma ray bursts at that time. 1995, you'll see the year was, so that's 25 years ago. It takes us back a little while. Just prior to writing that, a few years earlier, I was working as part of a group with the Space Sciences Laboratory with a fine astronomer there named Kevin Hurley. And what we were doing is we had access to an observatory at a telescope at Lick Observatory in the hills in the south of the Bay Area there where I was living in California. And this telescope we had access to because it was one of the last telescopes in one of the last professional telescopes in existence. I think it was the last professional telescope in existence that didn't use a digital camera, didn't use, and we were made the shift to CCD cameras, digital cameras, and that telescope was still outfitted to use photographic plates, the kind of things that had been used for the century prior to that, and they looked like this. So this is a photographic plate, and has an emulsion on there, and you would put this on the back of the telescope, and you probably can't see that in the light that we have, but there are dark dots on there that represent stars. And so these dark dots and that you see right there, that we would get these plates delivered to us. And what we were doing is we were doing fast follow-up to gamma ray bursts. And to say, could we see them in other wavelengths if we looked at them very shortly after we got the gamma rays? So we would get a gamma ray notification. The gamma ray notification would come in, and it would say, we've localized the position on the sky to this. Slew your telescope there to look at it. And so we would go look at this. We did not have the ability. We were way out of our league because for two reasons. We didn't have the ability with the telescope that we had to be able to see deep enough to see any kind of optical afterglow. There is an optical afterglow to these things, and we've seen them a lot since that time, since the 1990s. But we didn't have. We didn't have a sufficient telescope to be able to do that, and our reaction time was too slow. It took us 4 hours or so to get to the field of view where the gamma ray burst was occurring. Excuse me. Chalk dust. Inhaling chalk dust here, and dust from these old plates. And so you've got, we weren't fast enough and we weren't seeing deep enough to see these optical afterglows. And the reason for this, once we discovered the optical afterglows, is it turns out that these optical afterglows, the optical light that was there for just a little while after the gamma ray burst, was really faint and associated with a really distant galaxy. So people who'd been dreaming in the 90s that these were part of neutron star halo around our galaxy, the optical afterglow studies showed that you would have a distant galaxy that looked like this, and often there would be basically a supernova. It would be associated with a supernova that was right there. And you could see it now in X-rays. You can see it in optical light as well, these sorts of afterglows. And you can watch these things disappear for a few hours after the initial gamma ray burst of gamma rays that you got. If you look at slide 12 in your PowerPoint, you see that there's really two distributions. You see a beautiful distribution, two histograms. We've been working with histograms some, and that's an excellent use of histograms right there, is to say that there are two types of bursts. Long bursts that appear at a peak in that histogram around, 50, 60, 70 seconds, and short bursts that appear around 0.5, 0.6 seconds, 0.4 seconds. So you have the very short bursts and the very long bursts. These that we're talking about right here actually turn out to be more associated with the long bursts. And we think our best model at this date is to think that these are a form of hypernova. And a hypernova is a supernova, but it's a supernova that goes straight to a black hole instead of a supernova that goes to a neutron star. And so it's a very intense, very high-powered supernova. And goes to this black hole, and these follow every one of these long bursts. Every one of them is in the disk of a spiral galaxy, a star where you have young stars. So in a region where the young stars can exist, and these high mass stars, remember, don't live very long, and they would have to go to hypernova, have to go to supernova, in a relatively short time after they were formed. And so we think that's what's going on with these, and it looks like a pretty good model. We can model these things pretty well. The short bursts, I think there's more disagreement about what those are. But the leading models for the short bursts would say that they'd be neutron star, or neutron star black hole mergers. So you have these things, and as we talked about with the LIGO results, with the gravitational wave results of just the last few years, we know that those kinds of mergers are happening in the universe and happening with quite a bit of regularity. And so we expect that these might be making gamma ray bursts that we would be able to see out there. And so these sorts of things, this is a great example of the sort of current astronomy. We're going to talk about examples next week of things that we're studying to say, it takes a lot of effort, and over the course of 5 or 10 or 20 or 50 years, you can see this thing move and start to understand these objects. So these are objects, and this is why your book would have these in the black hole section. These are objects that are associated with black holes, often one way or another, either this hypernova or a neutron star black hole merger, or a neutron star merger. So with dense stellar remnants, they do appear to be associated with stellar remnants and not with. So, for example, these bright objects are not associated with the supermassive black holes that are at the centers of these galaxies. They're always out in the disks where young stars live, and so that's really the best reason we have to believe that these are associated with the collapse of a young star. So we see these things out in the disks of these galaxies, as opposed to the short bursts. The short bursts can be not just in the flat disk of the galaxy, but if you look at the galaxy side view like that, something like that, they appear to be in a halo around here. And so these are probably older objects that have been ejected from the disk and are out in a halo around the galaxy. And that would be more consistent with neutron stars and black holes out in there, things that have been lurking around for quite a while and maybe got a kick when they were formed. So if you formed them and you gave them a kick, you can kick them out of the disk of the galaxy, and they start to form a bigger halo around here. And so that's the idea of what these things are. But they really are helping us probe distant galaxies, because these are coming from all over the place and in very, very distant galaxies. So these are enormously energetic because they're really bright, a lot of energy associated. We measure a lot of energy with these gamma ray bursts, but they're very distant events that are going on in these galaxies. So they must be extraordinarily luminous in order for us to see them as brightly as we see them from as far away as we see them. So that's our introduction to gamma ray bursts. We waited until now to talk about it because of the galaxy aspect associated with the disks of galaxies, and that's what we've just been talking about here, is our understanding of the Milky Way as a spiral galaxy, and then our understanding of the Milky Way as just one of hundreds of billions of galaxies in the universe, and then the disks of spiral galaxies being associated with young stars, and that's where we see these long gamma ray bursts, and then the halo around these spiral galaxies, around any galaxies that we would see the short bursts. And so I think there's still work to be done in the gamma ray burst field, but since I wrote this dissertation 25 years ago, or was working with these plates from Kodak 30 years ago, the field's moved a long ways. And so this is an example of how we can really grow our understanding of these things. Always open, our model of science, always open to reinterpretation, and this could change anytime now. This could pop up. Fun note, I don't think I have it anymore. I think I've lost it. One of these boxes of plates, I have a few boxes of plates kicking around here, and I suspect it may be still around here. One of these boxes of plates, we were still getting gamma ray burst afterglows down in here, and one of these boxes we opened up, and there was a note in here from Kodak saying, hey, this is the last box of plates that we own. We're not going to make any more. Have fun with it. And so we got the last box of photographic plates for astronomy that Kodak ever made. And shortly thereafter, the telescope we were using would have been converted to a digital camera, like all of the other telescopes in the world at that time. So we were using it until we ran out of plates, and then Kodak stopped manufacturing plates, and we stopped using it, and astronomy became digital from that point on. Thanks, everybody. That's our topics for Friday, November 13th. We got 3 of them out there. Let me know if you have any questions.